Okay, with our last section, we worked on Ka expressions, Kb expressions, did some math to figure out pHs. Do the same thing today, but with just a little bit of an extra twist on it. So the twist is going to be primarily having some stoichiometry before we actually get to the equilibrium. So here is a typical acid-base stoichiometry question, and we already know all these parts, but if we wanted to solve the pH of this question, we have to see which one of these doesn't run out first but is in excess, and that excess amount we are going to use then to get to the pH. And I do have those steps here broken down in a little more detail, but I think it might be easier to just jump into one of these questions. So we have a hydrochloric acid, H positive, and we have sodium hydroxide, OH minus, and we're told to find the pH of this. By the way, with a number of questions that we're going to deal with today, I ended up using the same volumes and molarities. So the very first thing that we're going to do, and since many of these questions today use this same volume molarity setup, I'll just do the work for it here, and we can go back and revisit these answers as needed. Okay, so the hydrochloric acid, or H positive, is 2 times 10 to the negative third, and then the same work, we'll just put a little division here, the same work for the hydroxide, different answer though. So I think it's evident that the hydronium, the H positive, is much greater than the hydroxide. So we're going to typically, well, not typically, we're going to run out of the OH minus first. We'll have H positive left over. I wouldn't always write this out, but we're going to write it out in our first question here. Now this is ICF because this is stoichiometry, not equilibrium. And in these ICFs, we're going to use moles, but what's supposed to go in the ICEs are molarities, because when we get to the expression, we'll put molarities in for those. So we have, I don't have enough room to put the sig figs in here. But we have none of the hydroxide left. We don't care about the water in this case, but it's a 1 to 1 to 1. So wherever we have 5 times 10 to the negative fourth, we're going to add, or not add, but we're going to put 5 times 10 to the negative fourth everywhere else. And that is the moles that we have of hydrochloric acid. To get pH, though, you need concentration. So what is the concentration? The concentration is the moles divided by the total volume. And that molarity comes out to be that for hydronium. Take the negative log. And we'd get that. Okay, so we're going to use a lot of that same idea for lots of the questions that we're going to run into, and kind of keep in mind that I've already figured out the moles, so I'm not going to do that each and every time, because we're going to use the same volumes and molarities. If, when you do one of these questions, if it's not a strong acid, strong base, and you make other products other than water, you might get a situation where when you're all done, like here's a weak acid, strong base, you would make A minus. So you would always make the products, and maybe you have HA left over. If that's the case, you could, we'll go up to this top item in a second here, but you could go Ka equals A minus. Actually, let's change this. So if you end up running out of OH minus and making A minus and having HA left over, you really have, we'll put it back to how we had it in earlier sections, you would have that going back and forth in the beaker. And that is a Ka expression. H positive, A minus, HA, and we could solve for any of those parts. Typically, we'd be solving for the H positive part to get a pH. Well, you can always do that, by the way. But you could also do this. So if we have a Ka value, take the negative log of it, and that's a pKa, and then attach your A minus and HA. And by the way, typically these are molarities because it's brackets, but if you put the moles in here and you put the moles in here, these are in the same beaker, so they're going to be divided by the same volumes, which means that if you kind of disregard the volumes, it's not going to make any difference. So that makes it a little bit easier in these questions. So technically molarities belong, but because they're both divided by the same volumes, because they're in the same container, we can use moles in these situations. If we would use this, we would need a Kb. Okay? So we'll have to keep that in mind when we get there. Okay, so acetic acid and sodium hydroxide. So we have, by the way, you could always write acetic acid out, or you could always write this generic HA. That is a generic weak acid. We have our strong base, and that makes H2O, which in regards to pHs won't have any impact, and it makes A minus. Remember that we have the same volumes and molarities that we used in the previous question. So we have 2 times 10 to the negative third. We had 5 times 10 to the negative fourth. 0. These numbers will look somewhat familiar because we saw some of them last time. So we have HA left over, and we made A minus. So we could either go for that Henderson-Hasselbalch, that pH equals pKa idea, and let's do that since we haven't done one of those yet. Or you could always do the Ka equals hydronium times A minus up top, and then the HA on the bottom. Okay, and these are moles, but remember that they're both divided by the same volume, so you don't really have to put them in molarity because it's not going to make any difference in this case. We have a Ka, but we don't have a pK. So if you take the negative log of 1.8 times 10 to the negative fifth, you're going to get this as a pKa. So let's pop that in. And then we need our A minus up top and our HA on the bottom, and do that work, and we get a grand total of pH of 4.26. We don't know this yet, but if you have any solution where you have HA and you have A minus floating around the beaker, it's going to be very special. And We don't know why we're going to call it this yet, other than it has HA and A minus, but we're going to call that a buffer. We don't know any other definitions at this point what a buffer is. Similar situation, this time strong acid and weak base. So if you would have a situation where you have A minus left over and you make HA, well, there you go. You can still use the pH equals, not negative log, pH equals pKa plus log of A minus over HA. By the way, there was a misprint here. I had that said Ka for ammonia, Kb for ammonia. Same volumes and molarities, so a very similar setup. So ammonia is NH3. If you wanted to write A minus as a generic weak base, you could do that. And then hydrochloric acid is H positive, makes ammonia. ICF, like we've been doing, and we still have all these same numbers that we had before. Again, these are moles, and we could pop them into that Henderson-Hasselbalch like we did before, or if you don't like that, you could use a Ka or Kb expression. It's up to you. So we have a Kb, but we need a pKa, so that means we need a Ka. And if you remember, it is 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th to get a Ka. And I think that's going to be, well, I ended up doing all in one fell swoop, and I got to the pKa, and that was 9.26. Okay, so pH equals 9.26, that's pKa, plus log of the A minus, the base component, which is 1.5 times 10 to the negative 3rd, divided by 5 times 10 to the negative 4th for the acid component. So let's do that right now. 1.5 to times 10 to the negative 3rd, divided by 5 times 10 to the negative 4th. We'll take, probably should have done that without a calculator. I could have done that. Take the log of that and then add it to 9.26. Okay. So what is a buffer? This is the part that's important. Well, it's not the only part, but buffers resist pH change. And the reason they resist pH change is because they have both of those components, the acid, weak acid, and its conjugate base, or weak base and its conjugate acid. So if you would throw some hydroxide in there, it would get neutralized. If you would throw some acid in there, it would get neutralized. So that is how it resists pH change. As long as you have a significant amount of both the HA and A minus, you have a great buffer. If you have lots of one of those parts but hardly any of the other, it's not very good buffer. It's not a very good buffer. If you would take a salt, dry salt, and add it to water, it might impact the pH of the water. Sodium and nitrate would not, because both of those are not related to weak acids and weak bases. But this one here, If you would add sodium acetate into water, you'd get acetate, and acetate would impact water because it's related to the weak acid, acetic acid. It makes hydroxide by looking at this, and that would mean that the pH will go above 7. On the other hand, ammonium chloride makes ammonium, and ammonium would react with water to make that acid, well, the hydronium that's going to affect the pH, make it acidic. This is not going to be much in the way of test questions, but it's going to be important for you guys. We're not going to go into any of the details of these hydrated forms here. These are complex ions. Some people have some other names that they can call these things too, but if you would take a small cation, these are relatively small, and they're highly charged, it has the ability to attract lots and lots and lots of water, and in that hydrated form, you can have the ability to make this acidic. Okay, so just keep that in mind. So you wouldn't get that with, like, that wouldn't happen with lithium ions. But even though lithium's small, well, actually, let's make it a little more extreme than that. If we would take, let's say, potassium ions. Potassium ions are going to be too big and not charged enough to be able to do what the aluminum or iron plus 3 ions could do. That could either be no questions or 1 question on the test. Where does this happen for you, though? If anyone has these hydrangea at their house, you might have this situation depending on how much aluminum that you have. In this case, I think most Home Depot, Lowe's, they sell it as aluminum sulfate. If you have a lot of aluminum sulfate or very little aluminum sulfate, you can get a combination of the blue and the pink, purple, or you can get more of the blue or more of the pink. But this would definitely be test questions here, though. So predict. So I think we actually already did this one. So ammonium would interact with water to make ammonia and hydronium. If it makes hydronium, acidic. So I'll just go A. This one, Cn minus, interacts with water to make weak acid and hydroxide. That's going to make it basic. Oh, these are awfully difficult because now we have both of these items. The ammonium would like to make this thing acidic, but the acetate would like to make this basic. So let me write this out and show you what's actually going on here. Okay, so that's going to be a Ka reaction. We would need a Ka to talk about that. And then the acetate makes base, so we would need a Kb for that one. Well, Kas are given for both these, but really for that acetate we need a Kb. So if I did the Kb of this, 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th comes out to be 5.6 times 10 to the negative 10th. They're identical. So you'd have them both fighting out to a draw. And one of them makes an acid, one of them makes a base, but they'd make identical amounts of both of those. So this would actually be neutral. Not because they don't impact water, but they impact water at the exact same amount. Ammonium cyanide. the cyanide, the Cn minus, we need a Kb value. Remember, 1 times 10 to the negative 14th divided by 4.9 times 10 to the negative 10th. That is 2.0 times 10 to the negative 5th. Well, the Kb is much bigger, so it's going to produce more hydroxide than the Ka is going to produce hydronium. So this is going to be basic. We're not prepared to mathematically figure the pH of those out. We can do these ones though, that when there's only one component that impacts the pH. So acetate plus water makes acetic acid and hydroxide. So we need a Kb value for that. I think I'd already figured that out in a previous question. And I think we've done enough of these now to know that it's 0 plus x is x, 0 plus x is x, and then the initial concentration goes on the bottom. So we could solve for x, and when we would do that, that's going to be the hydroxide. And then we have to turn that into a POH, and then turn it into a pH. I'm going to kind of speed this up a little bit because we've done these kind of questions a number of times. We've just haven't added all these steps. But I think I'm pretty confident that you guys can take the X value, which is hydroxide, and turn it into a POH and turn it into a pH. But the pH will be 5.13. No, it will not be 5.13. I wrote down the wrong one, and that we're going to talk about that too. That one is 9.11. Sorry. And how do I know that I had written the wrong thing down? Because acetate makes hydroxide, so the pH has to be greater than 7. And my first, what I first wrote down was certainly not above 7. Okay, I ended up writing down the answer for this ammonium chloride question. So ammonium chloride will have ammonium react with water to make ammonia and hydronium. And the hydronium is going to make this pH below 7. So the synthesis of an acid reaction, I need a Ka. And when I take 1 times 10 to the negative 14th and divide it by 1.8 times 10 to the negative 5th, I get 5.6 times 10 to the negative 10th. Okay, so 5.6 times 10 to the negative 10th equals x squared up top. Our initial molarity on the bottom, x equals hydronium, and then you can turn that into a pH, and that one was the 5.13 answer. Okay, we have a couple more maybe, I'm not sure. Let's see if we got anything else, and that is it.